In section 7.7, we're looking at complex numbers. Our work with radical expressions has excluded expressions such as the square root of negative 16 because the square root of negative 16 is not a real number. There is no real number whose square is negative 16. In this section, we discuss a number system that includes roots of negative numbers. This number system is called the complex number system, and it includes the set of real numbers as a subset. The set of complex numbers includes the imaginary unit. The imaginary unit, written I, is the number whose square is negative 1. That is, I squared equals negative 1, and I is equal to the square root of negative 1. To write the square root of a negative number in terms of I, we're going to use the property that if a is a positive number, then the square root of negative a can be broken apart as the square root of negative 1 times the square root of a. And then we know that the square root of negative 1 is I, so we end up with I times the square root of a. So let's go ahead and write some radicals with our new notation. For the square root of negative 36, the first thing we're going to do is split this into two separate radicals. We have the square root of negative 1 times the square root of 36, but the square root of negative 1 is I, and the square root of 36 is 6, and so we would write this as just 6i. For the square root of negative 5, again, we're going to rewrite this as two separate radicals. We have the square root of negative 1 times the square root of 5. And so we end up with I times the square root of 5. For negative square root of negative 20, let's go ahead and write this as two separate radicals. We have negative times the square root of negative 1 times the square root of 20. Well, we know that the square root of negative 1 is I, and the square root of 20 can be written as 2 times the square root of 5. And so I end up getting negative 2i times the square root of 5. The product rule for radicals does not necessarily hold true for imaginary numbers. To multiply square roots of negative numbers, first we write each number in terms of the imaginary unit I. Once we've done that, then we can proceed as normal. So let's go ahead and do some multiplication and division. We have the square root of negative 36 times the square root of negative 1. The first thing we want to do is write both of these in terms of I. The square root of negative 36 is 6i, and the square root of negative 1 is I. So we have 6i times I, which is going to give me 6i squared. And there was a second part of the definition of I that we have not used yet, and that is I squared is equal to negative 1. So we're going to rewrite this as 6 times negative 1, which is just going to give me negative 6. Let's go ahead and try another one. We have the square root of 8 times the square root of negative 2. First, we can rewrite the square root of 8 as 2 times the square root of 2. And the square root of negative 2 is going to turn into I times the square root of 2. Now we just multiply the outside pieces and the inside pieces together. And so on the outside we have 2i, and on the inside we have 4. But the square root of 4 is just 2, and 2i times 2 is just 4i. Let's go ahead and try another one. We have the square root of negative 125 over the square root of 5. So I'm going to rewrite the top as I times the square root of 125 over the square root of 5. I'm going to use the quotient rule and make this one square root. And on the inside we have 125 divided by 5. But that just simplifies as the square root of 25. And the square root of 25 is just 5. So we end up with 5i. A complex number is a number that can be written in the form a plus bi, where a and b are real numbers. So we always write the imaginary part second and the real part first. Notice that the set of real numbers is a subset of the complex numbers, since any real number can be written in the form of a complex number. We can write 16 as 16 plus 0i because it doesn't have an imaginary part to it. In general, a complex number, a plus bi, is a real number if b is equal to 0. Also, a complex number is called a pure imaginary number, or an imaginary number if a is equal to 0 and b is not equal to 0. So we can write 3i as 0 plus 3i, or I root 7 as 0 plus I root 7. When we talk about adding or subtracting complex numbers, we are going to add the real parts together and add the imaginary parts together. The same idea goes with subtraction. I'll subtract the real parts and subtract the imaginary parts. If a plus bi and c plus di are complex numbers, then their sum, a plus bi plus c plus di, turns into a plus c plus b plus d times I. Their difference, a plus bi minus c plus di, turns into a plus bi minus c minus di, or a minus c plus b minus d times I. So let's go ahead and add or subtract the complex numbers. We want to always make sure we write this in the form a plus bi. So always write your imaginary part second. We have 2 plus 3i plus negative 3 plus 2i. So we're going to add the real parts together. We have 2 plus negative 3 plus, adding the imaginary parts together, we have 3 plus 2 times I. And so now we just want to simplify. 2 plus negative 3 is going to give me negative 1. And 3 plus 2 gives me 5. So my final answer is negative 1 plus 5i. In the second one, we have 5i minus 1 minus I. The first thing we're going to do is we are going to distribute our negative to both pieces. And so we have 5i minus 1 plus I. And then we add our imaginary parts together. We have our 5i and our I. And then making sure we put the real part first, we have negative 1 plus 6i. Multiplying complex numbers. To multiply two complex numbers of the form a plus bi, we multiply as though they are binomials. Then we're going to use the relationship that I squared is equal to negative 1 to simplify. It's okay to leave just a plain I in your answer, but it's not okay to leave I squared. We always want to make sure we get rid of all the I squareds and replace them with a negative 1. So for this first one, 3i times 2 minus I, we're going to distribute the 3i to both pieces. And so that's going to give me 6i minus 3i squared. And then again, we need to replace the I squared with negative 1. So we have 6i minus 3 times negative 1, which ends up giving me 6i plus 3. And we always write this in the opposite direction, 3 plus 6i. Leave that imaginary part in the back. Let's go ahead and try another one. In this case, we are going to just FOIL this like they were two binomials. We're going to multiply the 2 to both pieces, and then we're going to multiply the negative 5 to both pieces. So 2 times 4 is going to give me 8. 2 times I gives me 2i. Negative 5i times 4 gives me negative 20i, and then minus 5i times I gives me minus 5i squared. Again, I have that I squared that I can replace, and in the middle we have like terms. So I have 8, 2i minus 20i gives me minus 18i, minus 5 times negative 1. This ends up giving me 8 minus 18i plus 5, and we can combine like terms one more time. And that's going to give me 13 minus 18i. Let's try another one. 2 minus I squared. First thing I'm going to do is I'm going to write this twice, and then I'm going to FOIL it just like I did in part B. So we have 2 times 2, which gives me 4, minus 2i, minus 2i again, plus I squared. We have our I squared that we need to replace, and we have like terms in the middle. So we have 4 minus 4i, and this is going to become a minus 1. And so we can combine like terms one more time, and we get 3 minus 4i. When we divide complex numbers, we're going to use complex conjugates. So a plus bi and a minus bi are complex conjugates of each other, so that when we multiply them, we get rid of that I completely. That's the goal when we divide complex numbers. We want to get rid of any imaginary parts in the denominator. So it's kind of like rationalizing the denominator when we talked about radicals. Works very similarly. So 2 plus I over 1 minus I. We want to multiply the top and bottom by the complex conjugate of the denominator, which in this case is 1 plus I. And so now we're going to multiply the top and the bottom. So on the top we get 2 plus 2i plus I plus I squared. And in the bottom we get 1 plus I minus I squared. So we have I squared again, and we have like terms in the top and bottom. But if you notice in the bottom we have an I and a negative I, so those are going to cancel. In the top we have 2 plus 3i minus 1, and in the bottom we have 1 minus negative 1. So I have my double negative in the denominator. In the top, we end up with 1 plus 3i divided by 2. And we are going to go ahead and split these apart so that the real part is by itself and the imaginary part is by itself. So our final answer is just going to be 1/2 plus 3/2 I. Looking at 7 over 3i. You could think of 3i as 0 plus 3i, and so the complex conjugate of it would be 0 minus 3i, or just negative 3i. So we're going to multiply the top and the bottom by negative 3i. So in the top, we're going to get negative 21i, and in the bottom, we get negative 9i squared. Again, we have our I squared that we need to fix. So negative 21i on the top, and in the bottom, we have negative 9 times negative 1. So this gives me negative 21i over positive 9. And so we can actually simplify this a little bit by dividing by 3. This gives me negative 7i over 3. And so the way that we would write this is we still have to have our real part, which is 0 minus 7/3 I. And the last thing we're going to talk about is finding powers of I. So we can use the fact that I squared is equal to negative 1 to find higher powers of I. So to find I cubed, we can rewrite this as a product of I squared and I. So I cubed equals I squared times I, but I squared is negative 1, so this gives me negative I. Same idea goes for I to the 4th. This is just I squared times I squared, but that's really just negative 1 times negative 1, which is 1. And so we can keep this process going for anything higher to simplify I to the 5th and I to the 6th. If we continue finding powers of I, we generate the following pattern. Notice that the values I, negative 1, negative I, and I repeat as I is raised to higher and higher powers. So every 4, you'll see that the pattern repeats. So for example, if I wanted to find I to the 22, I'm looking for powers of 4. Well, I know that 4 goes into 22 5 times with 2 left over. So I to the 4th raised to the 5th times I squared. Well, I to the 4th is 1, and 1 to the 5th is 1 times negative 1, which gives me negative 1. So let's go ahead and apply that logic to find other powers of I. We have I to the 7th. We want to rewrite this. I like to go with whatever the closest even number is that's less than it. So in this case, I to the 6 times I. Well, I to the 6 can be written as I squared cubed times I. And we know that I squared is negative 1 raised to the 3. Negative 1 to the 3rd power is just negative 1. And so we end up with negative I as our answer. There is no wrong way to do this. You could split this up as I to the 4th times I cubed, and you would get the same thing. So for I to the 20th, it's already an even number, so it makes our life pretty easy. I'm going to use my base of a squared again, but this time it would be raised to the 10th. Well, I squared is -1 raised to the 10th, and a negative raised to an even power gives me a positive number. So we end up just getting +1. The same thing's going to happen for I to the 46. It's already even. So if I use my squared, that means I'm going to be using 23 as my next power. And so -1 raised to the 23rd is going to give me -1 because 23 is odd. And for this last one, we want to use our exponent rule where we flip negative exponents over the fraction bar. So this is going to become 1 over I to the 12th, and then we can keep the process going. Simplifying I to the 12th, I'm going to use I squared and raise that to the 6th. Well, we know that I squared is -1. And -1 to the 6 is going to give me +1, and 1 over 1 just gives me 1.